Hello there, guys. I am Mr. Noodlecup, and today we are going to learn about reactors, fission, and fusion. Let's all first begin with fission. So here we have a brick on the glass table. This could be used as an example for fission. This is the process of fission before. And this is the process of fission after. Let's show ourselves some credible sources about fission. So, the links are in the description because I can't fit them in these boxes. What is fission? According to Science Insights, fission is the separation of a heavy atom's nucleus that rips apart to two small nuclei, producing an enormous burst of energy and progress. One uranium-235 atom that gets torn apart produces approximately 215 million electron volts of energy, heavily 10 million times extra energy than lighting one molecule of fossil fuel on fire. This reaction charges every commercial nuclear reactor on Earth and invents isotopes used in medicine, industry, and research. Top 3 facts about fission, according to the Understand Energy Learning Hub. Number 3. The byproducts of nuclear fission are immensely radioactive and have to be shielded away from all people for hundreds and thousands of years. Yes, you are shielded away from nuclear radioactivity. So please, don't go there. It is sorrow's domain, but green. Let's get back to our facts. Number 2. The risk of accidents is small, but the consequences of one in a nuclear power plant is seriously severe. Number 1. Because of the complexity of having a nuclear reaction and the requirement of redundant safety systems, capital and operating funds are large, and there are extended lead times for planning and construction.
Yeah, this can take a lot of money to build at least 928 houses with
wood, bedrock, glass, iron, styrofoam, bread.
That's 2 credible sources for fission, but only one that's against. Safety and security from fission, according to UCS. The Fukushima disaster of 2011 revealed what occurs when the safety systems of a nuclear power plant get ruined. The nuclear industries of the United States informed with familiar reassurances that would not happen there. We learned better, imposing fire and earthquake regulations and safer local storage for nuclear waste are just a little bit of these ways we can help avoid nuclear accidents. Since its founding in 1969, UCS has obeyed as a nuclear safety watchdog. We help ensure that the NRC enforces its regulations for safety, and we try to avoid them from decreasing safety standards and error in response to industry pressure. We claimed that a well-controlled nuclear industry is in everybody's best interest, especially the industry itself. Misfortunes are not potentially threatening to nuclear facilities. A complete terrorist attack can kill, sicken, and displace heavy numbers of humans and emit large-scale, long-term environmental pollution. Securing nuclear reactors and screening nuclear material should be an intermediate concern for everybody interested in nuclear power. Unfortunately, the NRC has appropriately downplayed the attack of nuclear terrorism, calling its requirements for protection exercises in response to industry pressure to smaller costs. So, if you have your own locker room in your house, and you see B170, the guy who was radioactive, Lock your doors now. He's spreading nuclear radiation into your locker room.
Move all your lockers to the basement. Lock your basement door.
And subscribe to Mr. Noodlecup. Let's get ready for the next type of nuclear reactor, fusion.
There are so many good examples of fusion.
Such as N455 from Rooms Reestablished, which is a fusion of N55 and N400.
N455 has the same accident as AZTF from Orin Ayo. Let's look at some credible sources for fusion.
Research capabilities of fusion, according to NSF. Along with speculations in projects, NSF provides validity to chopping-edge research facilities that encourage foundational research and speed up real smarts critical to fusion development. The UCLA Basic Plasma Science Facility, a U.S. public research facility provided by NSF and the U.S. Department of Energy, supports an entrance to unique instruments, including its large plasma device that help researchers know about properties of magnetized plasma and learn how plasma might act in a fusion reactor with magnet confinement. The MAG Lab, collected by NSF and the state of Florida, is planet Earth's largest magnet laboratory. It holds over 75 powerful magnets, having the Guinness World Records class for strongest continuous magnetic field, closely 1 million times stronger than Earth's magnetic field. MagLab gives opportunities to researchers from colleges, national labs, and industry working to enhance the use of magnets for large-scale fusion energy.
This is enough for Magnet-Shroom to lift 10 million metal buckets after drinking a Vandermorn potion. To become CG55 himself. Let's continue. The NSF Zeus is found at the University of Michigan. As of its accomplishment of 2025, it's the highest powered laser system in the US. This and other powerful instruments supply world-leading research capabilities to study laser plasma interactions, advancing knowledge that informs the creation of interior confinement fusion. Conclusion of nuclear fusion research. According to World Scholars Review, attaining nuclear fusion on Earth presents two main potential types of confinement fusion, inertial and magnetic. Inertial confinement depends on high-energy lasers to squeeze fusion fuel, offering positive occurrences that include fast energy release and potential for shorter reactors. However, it encounters specific challenges that include asking for precise symmetry in constriction, which is difficult to earn consistently, and the small duration of fusion reactions, decreasing its triple product. NIF is now researching ways to grow energy output for ICF after recently grabbing a net power output. On the other side, magnetic confinement fusion employs magnetic fields to enclose plasma with tokamaks and stellarators as important designs. Tokamaks like ITER aim for continued operation and have revealed progress in earning sustained plasma temperatures and confinement times. However, they face issues including plasma asking for better confinement stability through complex magnetic field configurations, and counter challenges related to their complex design and computational demands. Research with the Wendelstein 7X stellarator is in progress and aims to address these issues. Now, magnetic confinement fusion, particularly between tokamaks like ITER, shows itself more promising due to its apparent simplicity relative to inertial confinement schemes and stellarators, possible for sustained energy manufacturing, and multitude of research and technological enchantments. Overall, though, the answer to challenge to implementation for both of these types of confinement fusion comes to remains earning sustained plasma stability below extreme conditions important for efficient energy production. Fast facts of fusion, according to GAO. Nuclear fusion could make electricity without carbon productions or long-lasting nuclear slop. A 2022 experiment earned a key milestone on the path to workable fusion energy. It's the first experiment in which the fusion reaction created more energy than that injected into it. However, this technology encounters challenges before making commercial energy. For example, new materials were asked to be developed that withstands the extreme conditions noticed inside a power plant using fusion energy. In that technology assessment, we've created policy options that helps you address such challenges. And this is the end of our fusions sector. If you liked this video, be sure to hit the subscribe button. And I'll see you next time. Bye!